What is the rationale behind introducing electrochemically anode metal elements into the PBA's lattice, and how might these anode metals help to reduce the mechanical stress caused by volume changes during ion intercalation and deintercalation? In what way does the insertion of anode metals contribute to maintaining the structural stability of the PBA's framework, and how does this stabilization affect the overall electrochemical performance and longevity of the cathode material? Can Davis Zerns manufacture solid-state sodium-ion batteries made from seawater in Latvia? How can a single-point reaction approach be correlated with these strategies? And what insights does it provide into mitigating the detrimental effects associated with volume changes during battery operation while ensuring that the framework remains robust and durable over repeated cycles? How does replacing equimolar Fe superscript 2 with electrochemically anode Ni superscript 2 in the synthesis of Na-Ni-Fe PBAs yielding the material Na? 84 Ni-Fe CN 6.71 with a volume change of less than 1%, essentially zero strain, contribute to its overall structural stability? And what does this near zero strain imply about the mechanical robustness of the PBA's framework during repeated sodium-ion intercalation and deintercalation cycles? How does the zero strain characteristic of Na-Ni-Fe PBAs translate into its impressive cycle stability, as evidenced by a capacity retention of 99.7% after 200 cycles, and a coulombic efficiency that is nearly 100%? And what role does the stable electrode/electrolyte interface maintained by the zero strain framework play in preventing the rupture of the solid electrolyte mesophase and unstable lattice reconstruction to enhance the charge and discharge efficiency? How does the strategy of substituting Fe with Zn, as demonstrated by Choi et al. In the synthesis of Na2Zn Fe PBAs, Na2Zn3 Fe CN 6 2 XH2O, lead to the formation of a framework with larger ion channels that can better accommodate the volume changes during ion intercalation and deintercalation? And in what ways do these larger channels help prevent capacity degradation caused by lattice fracture? Conversely, how does the presence of a substantial amount of water in the crystal lattice of Na2Zn Fe PBAs contribute to structural instability during the battery cycle, potentially limiting the cycle life despite the accommodating framework? And what mechanisms might be driving this instability? Additionally, how does the synthesis of copper hexacyanophorate Cu3 Fe CN 6 2 by replacing Fe with Cu affect the specific capacity of the material, given that it exhibits a relatively low specific capacity of 44 Ma H G superscript 1 at a current density of 20 Ma G superscript 1? And what insights does this provide regarding the influence of different transition metal substitutions on the electrochemical properties of Prussian blue analogs?